This is question 3 on June 2018 paper. It's a constant acceleration question. So you have a cyclist, starts from rest at the point O, a straight horizontal road. Cyclists move along the road with constant acceleration of 2 meters per second square for seconds, and then continues to move along at a constant speed. When the cyclist stops accelerating, motorcyclist starts from rest at the point O and moves along the road with constant acceleration in the same direction. And when the motorcyclist has been moving t seconds, then overtakes the cyclist. First thing they ask, and that's quite common, is to sketch, and on the same axis, the speed time graph for both of them. So remember, when you draw when you sketch the speed times graph, the marks will come for two things usually: for the shape of the graph, but for the values that you know as well. So you please remember, label the axis and put all the numbers that you know, or if they are not even numbers and they are letters, you put them, like t. They say the time is t, you put t. So this is the velocity, and this is the time. And I'm going to start with the cyclist. So the cyclist, when t is 0, starts from rest. So it's going to start here and accelerates for 4 seconds at 2 meters per second square. So this first part is going to be something like that, a straight line up to, we say, we don't know the final speed yet, but we know this is 4 seconds, and the acceleration is 2 meters per second. So if the acceleration is 2 meters per second squared, meters second square, and we know is the gradient of this line, acceleration is the gradient, that means that this is 4 and the gradient is 2, this is going to be 8, right? So we can write this value because it's not difficult to find. And then it's going to be constant speed. They don't say how long, right? So they say, and then continues to move along the road with constant speed. So this is our cyclist. We are going to write C for cyclist, for example. Then the motorcyclist start from rest. So it's going to start from rest, any point here, because velocity is 0, right? But later. So they don't start at the same time. They start with constant acceleration of 4 meters per second in the same direction. And it says when the motorcyclist has been moving for t seconds when she overtakes the cyclist. So at one point, our motorcyclist accelerates from rest. So after the other one, I'm going to write an M for the motorcyclist, and they will catch up when time is t. They will overtake when time is t. Actually, it's not t. If you read, they say the motorcyclist has been moving for t seconds when she overtakes the cyclist. So this is not t. What is t? Let me show you. What is t is really the time that the motorcyclist has been moving. So this is t, not the other time. This time here really will be t plus 4. Be careful with that when you represent in the graph. So okay, so this is the graph that you have to sketch, right? This gradient should be actually greater because it's 4 meters per second square, and this one is 2, so this one should be probably less inclined and this one more. But don't worry about the accuracy of the gradient. The important thing is that the shape, so the marks will come from the shape, right? And the numbers that you know. So this should be 4 and this should be marked as t, or t plus 4, right? So this is the first part. The second part says find, giving your answer to one decimal place, the value of t. What do we know to find the time that they have been moving? We don't really know much things. What we know And always keep that in mind when you are working with velocity time graphs, because it's very, very likely that you need to use that knowledge, is that the area under both graphs must be the same, because the distance that both have moved is the same, right? They start from the same point, just one after the other, but from the same point. And I'm not going to say. So this is the cyclist, the blue one is the cyclist, the red is the motorcyclist. The distance is the same, so the areas must be the same, and we are going to play with that. So the distance for the cyclist, so I'm talking about the blue one, is a trapezium, right? So the area of that trapezium is going to be, this side is t plus 4 plus t, which is this side, times by the distance, which is 8. So I have t plus 4, one side of the trapezium, the other side, divided by 2, times by the distance between them. So thus the area or the distance for the cyclist must be the same as the area for the motorcyclist. And the area for the motorcyclist is this triangle. And this triangle is going to be base times height divided by 2. We know the time, or at least we need to find it, but can we know this height? We can, because we know the acceleration. So I say the acceleration is 4. So if the acceleration is 4 and is the gradient, the acceleration is 4 and is the gradient, it will be the change in y. So it will be the final velocity, really, the change in y, v, divided by t. So we can say that the final velocity is 4t. So this distance here is 4t, is the final velocity. So we are going to use that to find the area of the triangle. The area of the triangle would be base times height divided by 2. Right? So we have one equation with one unknown, which is t. We can rearrange this a bit. So we have, in the left hand side, we have 2t plus 4 divided by 2 is t plus 2 times 8 is 2t squared, or 80 plus 16 is 2t squared. When we solve this quadratic equation, you will get one positive t, which is 5.5, and the same value but negative. And as the time cannot be negative, we just choose the positive one, right? To one decimal place, please remember to check if they are asking you something like that. So that's how we do this exam question. We just consider the areas under the graph the same, and that's quite common. Yeah, every time you have velocity time graph and they ask you to sketch, it's very likely that you have to use that concept, that the area is the distance, right? And that's this question.